Okay, so we defined a saturated water vapor pressure for a reason. We look for what we call saturated adiabatic lapse rate. We looked at dry adiabatic lapse rate. Obviously, there's a counterpart when you have water vapor in the air parcel that we are lifting from the surface, right? So what happens? Essentially, the change in heat. When you have a dry parcel, even if it expands or compresses, temperature changes, but there is no heat gained, right? Because it's adiabatic. Whereas here, even if it's adiabatic, as it rises and expands or compresses, you're going to change the water vapor. So you're going to have minus L dq. dq is the change in saturated humidity. L is the latent heat of condensation. It's a minus sign because if humidity decreases, then there is going to be heat released. If humidity increases, then there is no condensation, then there is evaporation, so you get heat loss, right? That's a simple way to think about it. So let's go back to our second law of thermodynamics. Delta Q, it was du plus dw. You remember, work done by the pressure force and done against the volume change, by the volume change against the environment, and internal energy change. So it was R plus CV, which is Cp times dt, the temperature change, minus dp over rho. So expanding or contracting corresponds to the energy done, loss versus gain, right? So Cp dt minus dp over rho, and we are setting delta Q equal to 0 because this is internal. With the environment, there is still no exchange. Internally, you are producing a condensation heat. So in the dry adiabatic case, we had Cp dt equals dp over rho, whereas in the moist case, you are going to add a term to the change in temperature in addition to the work done against the environment. You are going to have condensation heat release, right? So dp over rho is minus g dz. From where? Do you remember? Obviously from our hydrostatic balance, right? That never goes away. So you add that, dp over rho, you replace by g dz. So you're going to end up with Cp dt plus Lq. So, sorry. Take the d out, differential out, and then write it as Cpt. We're assuming Cp is constant. We're assuming G is constant. So you got Gz plus Lq. So d Cp dt plus G dz plus L dq is written as basically d differential of delta of Cpt plus Gz plus Lq. And this is called moist static energy. Moist static energy. Obviously, just this part is dry static energy. Okay, so turns out to be a very important variable, very important concept. So the saturation humidity is obviously a function of pressure and temperature, as we know. So you can write dq star by using law of partial differentiation. dq star is the partial q star partial p, variation of q star with respect to p times dp plus variation of q star with respect to t and dt. So this is the total derivative is the sum of these two, because those are the variables that contribute to the variability of q star. Okay, so q star is also rho v over rho, which we already did. So it's ES over RVT from ideal gas law over divided by P over RT, the air, so water vapor and air. So we already wrote this as R over RV times ES over P, and ES, saturation water vapor pressure is a constant in pressure units times e to the beta t, where beta is a constant 1/degrees, and temperature. This is the exponential dependence of humidity or water vapor pressure on temperature. This is our favorite Clausius-Clapeyron, right? So you can do d dt of this and get des dt to be beta es, because you will get beta e to the bt, right? I think you know how to do that differentiation. So e to the bt, a e to the bt is again es, so you can des dt can be simply written as a times beta times e to the bt, so that becomes beta e to the s. I'm not deriving these things, but you should probably go through those because they are simple but also very useful to do it yourself. So now you write q star again using various relations. dq star dp can be written from the previous relation. So dq star dp can be taken from here in terms of dq star dt and then plugged in. So dq star dp then becomes minus r or rv times es or p squared. So this is the same thing with es or p squared, and you can use the expression for q star to write it as minus q star or p. So q star is this times es or p, so you replace this over p with q star. What do you get? dq star dt is r over rv 1/p des dt. That's equals r over rv beta es over p from the previous equation, and that's equal to beta times q star. Okay, so you have expression for dq star dp as minus q star over p and dq star dt as beta q star. Obviously we can go back to this relation when we have this and this, right? Pressure dependence and temperature dependence of saturation humidity. So you plug it back into 426, which was basically our thermodynamic equation with delta Q equals 0. So we have Cp dt equals dP over rho minus L dQ, and dQ here is just dQ star. We're dealing with saturated lapse rate, saturated adiabatic lapse rate. So dQ star dt can be written as this. We already saw that. I'm just repeating so that you don't get lost. So you can get dP dt out of that. Manipulate, go easy on yourself and make sure you follow the steps. What do you get? Plugging into this relation, Cp dt plus minus dP over rho plus L dQ, you get Cp plus L beta Q star times dt equals dP over rho times 1 plus LQ star rho over P. We're just manipulating the relations using ideal gas law and so on and so forth. Right? So dP over rho is again minus g dz, our good old hydrostatic equation. So you end up essentially with dt over dz. Okay, replace dP over rho with minus g dz, take dz on this side, you get minus, take the minus sign on the other side, minus dt dz. Why? Because pressure, temperature decreases with height, so we put the minus sign over there and make it gamma s, which is saturated adiabatic lapse rate, is a function of dry adiabatic lapse rate times 1 plus LQ star or RT, saturation humidity, latent heat of condensation, and RT, divided by 1 plus beta LQ star over Cp. So saturation adiabatic lapse rate is related to the dry adiabatic lapse rate through the moist processes. Okay, so we will see that if the air parcel has water vapor in it, as it begins to rise initially till the water vapor actually condenses, it behaves just like dry air, and then it will behave like moist air because you have to account for the latent heat released by water vapor. Looks complicated, but it's not, so just go through it again, make sure you understand.